Hey guys, welcome to video 92. Today we're going to start talking about tone stacks or tone controls for amplifiers, and we're going to begin with a little bit of review of the basic first order low pass and high pass RC filter sections. If you want to see some more detailed analysis of these, go back and review videos 24, 25, 26, and 27. Starting first with the low pass filter, if we come to the center of the page, we've got the equation for the transfer function or response of the filter. This is in polar form, so we've got the magnitude and phase angle, and it's given in terms of the ratio of the input frequency to the critical or corner frequency f sub c, which is given by 1 over 2 pi RC. And you might remember that this is the frequency at which the magnitude of the capacitive reactance X sub C equals the resistance in the circuit. Now, coming back to the center of the page, we've got a graph of the magnitude of the response versus frequency. At 0 Hertz, the response equals 1. As frequency goes up, the response drops towards 0. And at f sub c, the response is down to 0.707. Now, most of the time when we're looking at filter response curves, we prefer to use a graph of the response in decibels versus the log of frequency, and that allows us to use these nice linear asymptotic response approximations to the actual response, which is continuous. At the corner frequency, the response is down by 3 dB, and remember, a first order filter will have a roll-off rate of minus 20 dB per decade, so for every tenfold increase in frequency past the corner frequency, the response will drop by 20 dB. Now, moving down to the lower half of the page, we'll take a quick look at the first order high pass RC filter. It's very similar to the low pass. We just interchange the resistor and capacitor positions. The corner frequency is still given by 1 over 2 pi RC, and the response equation is very similar to the low pass, except we invert the fraction. Now we're using the ratio of the corner frequency to the input frequency, and of course the phase angle is going to be positive or leading on the output in this case, as opposed to lagging in the low pass case. Looking at the graph of the magnitude of the response, we see at 0 Hertz or DC the response is 0. The capacitor is essentially blocking DC. And as frequency goes up, the response approaches 1. At the corner frequency, again, the response is 0.707. And as usual, when we're looking at filter response curves, we prefer to use decibels versus the log of frequency, as we have shown over here on the right. Now, there's a lot more filter theory we could get into here, including higher order filters and different responses like band pass and band stop and all pass. But if you have a basic understanding of the first order low pass and high pass, you can generally figure out pretty much what's going on in most tone controls. So let's just go on over to the next page and we'll start talking about the basics of where tone controls are located in the amplifier. In almost all cases, the tone control circuitry is going to be located between stages of the low power or preamp section of the amplifier. A more detailed view of that is shown down here, and one of the more important aspects of the tone control we need to know is its input impedance, so that we can tell how it's going to load this first stage. Now, the output impedance is also nice to know, but it's normally not going to be as significant as the loading effect on this first stage. For the purposes of this discussion, we're going to assume we're using vacuum tube amplifiers here. So that being the case, this first amplifier stage is probably going to have a fairly significant output resistance. If we were using a 12AX7 here, we'd probably have an RO of around 50,000 ohms or so. If it was a 12AU7, it would be significantly lower, maybe 10,000 ohms or less, but in either case, it's something that we need to take into consideration. Now, on the output, we're typically going to be driving an amplifier with an input resistance of at least 200,000 ohms, maybe as high as 1 meg, and that's why this voltage divider that we end up with over here is not usually that significant in our calculations. And what this means is that we want the input impedance of our tone control circuit to be relatively high to prevent significant loading and messing up the AC load line of this first stage. Now, if we were dealing with a solid state amplifier, there's a good chance we'd be using op amps in the amplifier, and they have almost zero output resistance, so loading and input impedance considerations on the tone control would be much less significant in that case. So let's go on over to the next page, and we'll start with the simplest tone control that you're going to find, and that's the basic treble cut circuit. In this example, we're assuming the amplifier driving the tone control has an output resistance of 30k ohms. The amp we're driving has an Rin of 470k ohms, and our tone control is simply a capacitor in series with a variable resistor. Now, when the wiper of the pot or variable resistor is all the way at the top setting, we're cutting the treble because we're just connecting a capacitor from the output terminal directly to ground, and this is going to severely cut the treble response of the amplifier. When we move the wiper to the bottom of its travel, we've got a relatively high resistor here, and it's going to have minimal effect on the output frequency response of the circuit. What it boils down to is we're forming a low-pass filter on the output of this first amplifier stage, and when the pot is set to the full cut position, the corner frequency of the filter is given by 1 over 2 pi Ro times C1. If we plug in the values for this circuit into the equation, we end up with a full cut corner frequency of about 240 Hertz. Now, there's no rule that says what this frequency has to be. That's one of the nice things about designing guitar amplifier circuits. You can do whatever you want. But typically, you're going to get a useful circuit if you set this frequency somewhere between the low E string frequency of about 82 Hertz and the high E string frequency of around 330 Hertz. All of the tone controls we're going to talk about have some loss associated with them, and in the case of this circuit, it's typically around 6 dB. And coming over here to the box on the right, keep in mind that we're typically also going to have coupling capacitors around the tone circuit. Sometimes it'll be on the left side, sometimes on the right, possibly both, but not always. But in any case, I'm going to omit those capacitors from these circuits just to keep things simpler. Now, let's take a look at the operation of this circuit using PSpice. To save some time, I've already drawn the schematic and set up the analysis. We're going to sweep the frequency of the input from 10 Hz to 10 kHz, and we're going to look at the response for 3 different pot settings. Once with the wiper all the way at the top, once with the wiper all the way at the bottom, and once with the wiper 10% down from the top. And the reason I'm using 10% rather than 50% is because in this application we'd want to use a log or audio taper potentiometer. If we used a linear taper pot, all of the action of the pot would be in the first 25 or 30 degrees of rotation, and we don't want that to happen. So I'm kind of simulating an audio taper pot here by using 10% down rather than 50%. Alright, now here is the result of the analysis. I've got decibels versus log of frequency from 10 Hz to 10 kilohertz. This green curve represents the pot in the upper position of the wiper. The blue curve represents the pot set all the way down at the bottom, and the red curve is with the pot 10% down from the top. And if we take a look at this green curve, we can see that the corner frequency is pretty close to our predicted value of 240 hertz. Yeah, maybe a few hertz one way or the other, but it's pretty darn close. And again, that's with the pot all the way set at the top of its rotation. If we move the pot down 10%, we get this red curve, so we can see that we're getting less treble cut. And if we move the pot wiper all the way down to the bottom, we've got the blue curve where the response is pretty flat all the way from 10 hertz on up. So here we have the simplest tone control you're going to run into, and this is one that also is used in most guitars. Over here we'd have our pickup and its winding resistance. This would be the capacitor in the guitar and the tone control pot, and this would be the input resistance to the amplifier we're connected to. Alright, so let's minimize our P-Spice stuff and go on to the next page and look at another simple single potentiometer tone control that's pretty interesting. What we've got here is basically a low-pass filter and a high-pass filter, and we're mixing the outputs of the two filters with a potentiometer. If we move the wiper to the left, we're going to be getting more of the output from the low-pass section. If we move the potentiometer wiper to the right, we're getting the high pass output, and in the center we should be getting roughly a 50-50 mix of the two filter responses. Now, unlike the previous tone control where we wanted a logarithmic or audio taper pot, this time we want to use a linear taper pot because we want equal mixing of both sides with the wiper exactly in the center. Now, the detailed analysis of this circuit is pretty long and messy, and I don't feel like getting into all that algebra today. So what we're going to do is choose R3 to be large compared to either R1 or R2. And if that's the case, we can more or less treat these two filter circuits individually without considering their interaction. So if that's the case, then the corner frequency for the low pass side is 1 over 2 pi R1 C1, and the corner frequency for the high pass side is 1 over 2 pi R2 C2. And the typical insertion loss for this circuit is somewhere around 6 to 12 dB. It depends on RO and RN, but just an estimate is somewhere in this range. As far as the overall design of the circuit goes, we have two options. I'm going to call the first one version 1. That's where we set the corner frequency of the high pass filter lower than the corner frequency of the low pass filter, and these are the two individual filter response curves here. Now, the second version, we just reverse this and set the corner frequency of the low pass lower than the corner frequency of the high pass, as shown by these two curves. And a third option would be to set the corner frequencies equal for both halves, but that doesn't give much of an interesting response, so we're not even going to bother with that one. Now, the curves I have here are nice for understanding what's going on in each side of the circuit, but what we really want to look at is the output here at the wiper of R3, and to do that we're going to use P-Spice. So let me bring up the schematic editor, and we've got version 1 here. I'm using a 25k ohm resistor for our source. RL is 470k, and the low pass section of the circuit has a corner frequency of 482 hertz. The high pass has a corner frequency of 100 hertz, and I'm using a 500k pot to couple the two sides of the circuit. And we're going to sweep the frequency again from 10 hertz to 10 kilohertz, and we're going to look at the response for the three pot settings all the way to the left, in the center, and all the way to the right. So the response curves we get look like this. Alright, this blue curve is with the pot all the way set to the left looking at the low pass filter, and the response we get does look pretty much like a standard low pass response, and the critical frequency is somewhere here between 300 and 400 hertz. Now, if we move the pot to the center, we get this red curve where we're down a bit at low frequencies, we peak in the mid band and roll off to about minus 12 dB or so at high frequencies. And finally, if we move the pot wiper all the way to the right and connect it directly to the high pass output, we get this green curve where we've got suppressed low frequencies, and we come up and look pretty much like a normal high pass filter with just a little bit of peaking here around 300 to 400 hertz. Now remember, none of the component values or corner frequencies I've chosen here are carved in stone. You can experiment with this all you want, and you could come up with something that works really nice for you, but this is a good starting point for a design. What we'll do next is take a look at version 2, so let me minimize this schematic and pull that one up. And you can see in this case I've got the same source and load resistance, but I've just swapped the corner frequencies for the two filters. The low pass is now 100 Hertz, the high pass is 482 Hertz, and we'll go ahead and run the analysis here, and we'll check to select our three sweep values, and we'll add our output trace, which is the drop across RL on node 2, but we want to express that as decibels, so I put dB in here, and there we go. Starting with the wiper of the pot set all the way to the left, connected to the low pass output, we're going to get this blue or purple colored curve that looks pretty much like a standard low pass response with a corner frequency of around 100 Hertz. Now if we move the wiper to the center of the pot, we get this red curve where we're down close to 10 dB at low frequencies. We dip down to almost 20 dB at around 300 Hertz. And then the response comes back up to about minus 12 dB at high frequencies. So we're getting kind of a scooped mid-range here, and some people like tone controls that scoop the mid-range, and if you do, this is a good choice for you. Now if we move the wiper all the way to the right, connected to the high pass output, we get this green curve where we're down near 20 dB at low frequencies, and then the response starts to climb back up at about 100 Hertz, leveling off at high frequencies at maybe 6 dB down. So this is another alternative. It's a little different than version 1, which gave us a little bit of a peak in the mid-range versus a scoop in the mid-range. So you can experiment with any values you want for these components and frequencies, and between the two versions of this circuit you should come up with something that works pretty well for you. What we're going to do next is take a look at another tone control that gives a scooped mid-range, but it works a lot better than this one does. So let's go on over to the next page, and here's the circuit. Now, since this tone control is designed specifically to remove the mid-range frequencies, we could call it a band stop or a notch filter. The circuit is shown over here. I'm using a 30k ohm output resistance on my driving amplifier. The input resistance of the amp we're driving is 470k, and we're going to make a few assumptions to make the analysis here work nicely. We'll assume that R2, the potentiometer, and the input resistance of the amplifier are both at least twice the value of R1. That makes our notch or null frequency equation more accurate. And to simplify the calculations a little bit and reduce the number of variables we have to contend with, we'll set C1 and C2 equal to each other, which gives us this simpler equation down here at the bottom. Now let's talk about the output resistance of the amplifier driving the tone control for a second. RO doesn't affect the frequency of the notch in our filter response, but it can affect the depth of the notch. The smaller RO is, generally the less deep this notch will be. If RO was equal to 0, we'd get a flat response curve and the potentiometer would just act like a volume control. But the circuit's relatively insensitive to changes in output resistance, so it's going to work the same way for a 12AU7 based amplifier with low output resistance than it will for a 12AX7 based amplifier with a high output resistance. And I'll demonstrate this characteristic in a bit when we do some P-spice analysis. And speaking of the null depth, generally, if we increase the value of R2 relative to R1, that's going to give us a deeper null depth or a deeper notch here as well. And on average, the typical insertion loss for this circuit is about 3 dB. So for the circuit, as I have shown here, our capacitors 0.0047 microfarad, R1 is 100K, R2 is 250K. If we plug those values into our null frequency equation, we get 214 Hertz. And as you can see here on the graph, this PSpice capture gave a null frequency of 207 Hertz. So they're in really good agreement. Now, just like the other circuits, there's nothing carved in stone about the values I have here. So let's go over to the next page and take a look at what happens if we change our potentiometer from 250K ohms to 1 megohm. If we plug these component values into our null frequency equation, we end up with a frequency of 107 Hertz. Now, again, I did a PSpice analysis of the circuit, and it gave me a null frequency of 105 Hertz, so we're in really good agreement here. So changing the potentiometer from 250K to 1 megohm decreased our null frequency from 207 Hertz down to 105 Hertz, and our null depth also increased from about minus 10 dB for the previous version to almost 20 dB for this one. And just to refresh your memory, here is the previous results we got. Our null depth was pretty close to minus 10 dB. Our null frequency was 207. Changing the pot gave us a null depth of almost 20 dB and a decrease of frequency to about 105 Hertz. Okay, now let's say we like this nice deep notch that we got changing the pot to 1 megohm, but it moved the frequency down too far. We had it originally at about 207 Hertz. Now it's real close to 100. So what could we do to move this notch back up to where it was? Well, we could decrease the value of R1. That would shift the curve to the right, but that would also shift the vertical spacing of these curves too. It would move them all up some. And if we don't want to do that, we just want to move the curve to the right, the better thing to do is to decrease the value of the capacitors. So if I cut these roughly in half using 0.0022 microfarads, the closest standard value to that, here's what we come up with. Here's the circuit in PSpice with the capacitors changed. The pot is still 1 megohm. And here's the frequency response plots that I end up with. Now notice that we still get a maximum notch depth that's pretty close to minus 20 dB. But now our notch frequency is increased to, what do we have here? About 225 Hertz, which is really close to what we had before, 207 Hertz. So that would probably work just fine. Another thing that I mentioned earlier about this tone control is that its characteristic curves are relatively independent of the value of RS. Here we've got 30K ohms, which is a pretty high value, and that might be what we'd get if we had a 12AX7 based common cathode amplifier driving this circuit. Now, if we were to switch to, say, a 12AU7, we'd probably get an RS value more like 5,000 ohms. So let's change this to 5K ohms and see what effect that has on the curves over here. So coming over, I already did the analysis run, and here are the curves. So these are the original curves. These are the curves with 5K in there. And you can see there's virtually no change in the curves at all, going from 30K to 5K. So that just kind of backs up what I said earlier, that this value of RS really isn't very critical in this circuit unless it gets really small. And that's very unlikely to happen if we're using typical common cathode vacuum tube amplifiers. Now, if we happen to be trying to drive this tone control with an op-amp, say, they typically have extremely low output resistance, close to 0 ohms, and in that case this tone control circuit wouldn't work unless we added an external RS here in series with the output of the op-amp. But that's a topic for another day. Okay, let's get these PSpice windows out of our way, and we're going to move on to the next page where we're going to take a look at some classic tone stacks that you're going to find in Fender, Vox, and Marshall amplifiers. Now, keep in mind that there are different versions of these tone stacks out there, and these are just three of the more common ones with typical values that you're going to run into. And I'm not going to use PSpice to analyze these ones. In this case, we're going to use a resource that you guys can go onto the web and download. It's on a website, Duncan's Tone Stack Calculator. Here's where it is, duncanamps.com/tsc/ and here's where you can download it, but I already have it downloaded and installed, so I'm going to open it up here, and here's the window we get, and you'll notice I've opened it to the Fender topology, which is shown over here, and we have the exact same component values except for our source resistance. In this case, in the tone stack calculator, it's 38K, where I have 30K. So let me change that. To do that, we can just double click on this signal source and change it to 30K, and it automatically updates the symbols and everything. And here's the curve for all of the pots set to their center of their treble. So you can see this thing is scooping the mid-range somewhere around around 500 hertz or so. And you can use these sliders to vary the pots. So the bass control here in the middle, if we move that from one extreme to the other, we can see how it changes the bass response. And the mid-range, likewise, and treble, the same thing. And we can move them all different amounts, different ways, and see what's going on. So this is a really nice tone stack calculator. And you can change the values of your pots if you want to. This 250K, we could change it to 100K. Right now it's a log type A pot. We could change it to linear or log type B, and we can do that with all the other pots. We could change the capacitor values by double clicking on them, and we can change our load as well. So this is a really handy calculator, and this is the response we're getting for this Fender circuit. Now in the center here we've got the Vox, so I'll move this over a bit and we'll open the Vox. It's the same topology here, and again we can look at the response for different settings of the pots, and if we want to, we can change the values of any of the components here. And lastly, here's the Marshall stack. If we click on that tab, we've got this circuit. Again, the source resistor is different here. I'd probably want it to match up with mine of 30K. And there we go, and we can look at the different responses with our pots in all these different positions. All right, so that's a really cool resource out there, and if you're going to be experimenting with these tone stacks, this is a really great thing to use. Now we're going to look at one last tone control circuit, and it's over on the next page, so let's slide on over there. And this is a classic. It's called the Baxandall tone control. This circuit is named after its inventor, Peter Baxandall, and here's his Wikipedia page. And as you can see, it's a pretty complex circuit, and I wouldn't want to try to analyze it using pencil and paper, but fortunately for us, it's available in the tone stack calculator, so we'll pull that up in a second. But a couple of things to notice. First of all, it's got a pretty high amount of insertion loss, about 20 dB, but it's got really nice frequency control characteristics. When the bass and treble controls are in the center of their travel, the response is pretty flat the whole way across the audio range. So if I pull up the tone stack calculator, here it is. In this, it's called the James topology, and as you can see, with the pots set at the middle of their travel, we've got a pretty flat frequency response. If we push the bass up, we get mostly bass increase and bass cut when we move it the other way. And if we go to the treble control, it gives us very nice control over each range individually without affecting the other. So that's one of the nice characteristics of the Baxandall tone control. It's got really flat response in the middle of the pot settings, and they only affect their respective frequency ranges. Now, you don't see the Baxandall used in very many guitar amplifiers, maybe because it's so complicated, but you do find it quite often in hi-fi amplifier applications. Now, as far as this tone stack calculator goes, there are some more topologies on here that we haven't looked at yet. There's this E series, and if we move up, we've got a bench filter, and this one includes inductors. It's, you know, pretty complicated, but it's got good performance, very flat, much like the Baxandall, probably a little bit better because we do have inductors. We've got the big muff, which is very similar to the original single pot tone control I talked about earlier in the video. And we've got a high watt, which is another complicated tone control. But in any case, this is, you know, as far as I'm going to go with tone controls for now. Hopefully you found something useful and interesting here. And that's it for today. So I'll see you guys next time around.